Hello, let's talk motion. Let's start out with simple motion. I define simple motion as an object moving in one direction at a constant speed without other forces or factors influencing it. An example might be a ball rolling across the floor, but it would need to be a relatively smooth floor so that we don't have to worry about friction slowing it down. If we're trying to show that motion is simple, we need to be able to isolate the object the best we can, moving debris out of the way, making sure nothing interrupts its path, give it a good push to start it going, and then determining if it is keeping a constant speed. So if you think about this, speed is how fast something travels over a given distance. So we would want to track the time it takes our object to travel several meters in a row, for example. And if it takes the same amount of time to travel each meter, then our object is moving at a constant speed and therefore undergoing simple motion. Here's an example of a test of simple motion. So this is the result of a test. A ball was rolled on the floor for 3 meters. Time was recorded when the ball was released and when it passed each meter marking. So we have the position in meters for 0, 1, 2, and 3, and then the time in seconds 0, 2, 4, and 6. And we can make a plot of this motion, which we see here. So we put the position on the vertical axis here, and the time on the horizontal axis here. And then our data points are the blue dots, and we can see that we get this nice clean diagonal line that all of our dots fall very nicely on. This clean line shows us that the object covered that same distance of 1 meter in the same amount of time, 2 seconds in this case. So that means if it's traveling over the same distance in the same amount of time, that means it was moving at the same speed, a constant speed. So this is what a position versus time graph of simple motion should look like. Now, don't worry if your definition of simple motion was different than mine, or if you didn't make a plot or anything like that. I mainly wanted to see what you would come up with. Well, let's hop into the rest of the lecture. In order to define position, we need to know several things. We need a reference point to measure the distance from. We call this an origin. The distance our object is from the reference point and which side of the origin the object is on. So we have this example here where the post office is the origin, and we're looking for your position, and you happen to be in this car that is 4 miles from the origin. But like I said, we need to know which side of the origin it's on. So you could say it's on the right side or east, because we're given east and west here in directions. So the position of you in your car is 4 miles east of the post office. Another thing to think about is instead of having to say like to the left or to the right, although I'll probably say that for a little while so we get used to it. We also we set a number line with the origin being 0, and then anything to the right of the origin is positive, and anything to the left of the origin is negative. So your car is positive 4 miles from the origin, and this cow is negative 5 miles. So those signs are telling us without saying left, right, east, west, they're telling us which side of the origin each of these objects is on. For horizontal motion, we'll usually use x as the variable of position. Um, for example, in this snapshot, we have a runner at 20 meters. We know it's 20 meters because here are the units given. So we have, okay, here's our variable x, which means position, and our units here is meters. So each of these on the number line represents a certain number of meters, and our runner is at 20 meters. if we use, I mean, we will, when we use vertical motion, we'll be using the y coordinate instead. And something that happens with vertical motion is a lot of times the ground can be set as 0. And then everything above that is some positive distance away from the ground. So our rock is just a little past 2 feet from the ground here. And you can also use the number lines for and the x coordinate specifically on an inclined surface, like as long as that surface is kind of straight. So it's just, I mean, you could literally like tilt the screen and then it would be flat again. And so we have this skier who's 10 meters down this slope. And again, meters because our units are labeled here, and just like it was feet here because that's the label we have. So I did introduce the idea of speed already a little bit with the simple motion thing, but officially speed is the distance an object travels divided by the time it takes for it to travel. And remember how we're thinking about equations, right? Is we are thinking about what it tells us about the relationships between these variables. So our variables are speed, distance, and time. And this relationship is telling us that the more distance you travel in less time, the faster you're going. Or let's say the distance doesn't change, but you take more time to travel the distance, that means your speed is less. In general, speed is going to be in units of meters divided by seconds. Sometimes you'll see like feet or something like that, but the kind of standard units for physics and for speed in physics specifically is meters divided by seconds. This is also referred to as meters per second, just like miles per hour. That's actually what it's saying. It's saying miles would be on the top and hours on the bottom. So there's different kinds of speed. There's instantaneous speed, so as it sounds, speed at any given instant in time. And then there's the average speed, which is the distance traveled divided by the time interval. So this is for if we don't know for sure that our speed is constant. We take the average speed, and that's kind of assuming that it is constant. And then there's velocity. So velocity cares about both the speed and the direction of the motion. Speed just cares about the value. It's just like, tell me how fast I'm going. That's all that matters. Velocity, we need to know both how fast we're going and what direction we're going in. So as I have labeled down here, 10 meters per second to the right. Or you could just leave it as positive 10 meters per second. And that's saying that it's going to the right. But for now, we should probably indicate direction. Oops, I want to skip that one. And constant velocity is when the speed and direction of the motion are unchanging. Like the simple motion discussed at the beginning, as long as the speed and direction were constant or unchanging, the velocity we had was constant. But keep in mind, there's two factors here, both the speed and the direction. So velocity could be not constant if either the speed changes or the direction changes. So like you could have someone driving around a circular track and they could drive at a constant speed the whole time, but because they're driving in a circle, their direction is changing, so their velocity is changing even though their speed is constant. And as I said, it matters which side of the origin an object is on. So again, the post office is our origin. We already talked about the cow and your car on either side. But it also is important to know the direction with respect to velocity too. So motion to the right, not just when our object is on the right of the origin, but when motion points in that direction, it is positive. like the velocity is positive. And when motion points to the left, the velocity is negative. So like, I mean, both of these are pointing in the direction, but let's say the cow was facing the other direction and was moving at a cow's pace toward the origin, toward the post office. That would make the cow's motion positive because it's heading to the right. But if the cow was facing the direction it is in this image, facing the left and started moving at its cow's pace, that would be negative velocity. So let's look at some ways to represent motion. We have snapshots of the motion of this car. In these, the same amount of time passes between each snapshot. And you can see that along with that being the same amount of time, it looks like the car has traveled the same distance too. So each car is the same amount of time apart. And just by looking at it, those distances also look the same. So if the time and distances are the same, that's simple motion for one thing, but that also means it's constant velocity. And let's walk through how to interpret these three different ones. So first we have a skateboarder. And it looks like, just like with the previous page with the car, looks like the skateboarder is traveling the same distance between each of these timestamps. So he's moving at a constant speed. He's showing simple motion. And then we have this runner, and her points are closer together here, and then she gets farther apart. That means she's speeding up or moving faster. And then we have this car, and the car kind of does the opposite of the runner, where it starts farther apart, and then these two here are practically overlapping or are overlapping points. So that's showing us, okay, it's going faster at first, and then it's slowing down and maybe coming to a stop. We can't quite tell. Now let's look at this diagram and think about which car is moving faster. How can we tell? So again, each image of the car is the same amount of time apart. And we can assume that with these two, they're also showing like they're to scale with each other, meaning that the yellow car's distance is clearly bigger than the reds, and we can assume that that means like translates to real life. So for these timestamps, the yellow car travels more distance than the red car, so the yellow car is going faster. These ramps here are also the same kind of motion diagrams where the same amount of time passes between each consecutive point. So we can see that as the ball gets toward the bottom of these ramps, they're covering more distance in the same amount of time. So looking at this just first regular one, they start really close, and then by the end, they're pretty far apart. And we can see that with each of these, that same kind of relationship, although maybe how far apart they get could look a little different. So Galileo did an experiment with different ramps. He was trying to see how an object acquired speed as it went down an incline. And what he found is that for each individual incline, the velocity increased at a constant rate. This doesn't mean between inclines, so it doesn't mean the rate of velocity increases the same between this first one and the second one, but it's saying that at each of these points, it's increasing by the same amount of velocity. And if the velocity is increasing at a constant rate, that means that there is a constant acceleration, because acceleration is how quickly the velocity is changing. Or when there is a change in velocity, it's telling us that there must be some sort of acceleration, because acceleration is what changes velocity. And as I said before, even in rotational motion, even going in a circle, the acceleration is changing when the velocity changes, even if the speed isn't changing. So like changing direction also requires acceleration, is what I mean. So Galileo found that the steeper the incline, the bigger the acceleration. And you can kind of see this with these diagrams. Like I said, I mean, it's like not entirely easy to see, but you can kind of tell that these last 2 points are farther apart than these two. And then you can definitely tell between like this diagram and this one that those points are closer together than these two. And that's the same amount of time. Covering more distance means they're moving faster. So Galileo found that the velocity acquired as a ball went down the ramp was equal, to the acceleration times the time. So let's look at that. Another equation. The velocity acquired equals the acceleration times the time. One second. So what this is telling us is that if the acceleration is the same, the longer the ball is rolling, the faster it's going to be going. And we saw in the previous page that the steeper the incline, the larger the acceleration. Well, what we saw was the larger the velocity got, but it was also the larger the acceleration. So here we have a tiny person dropping a ball off of a cliff, and we have speedometers here showing how fast the ball is, well, for these first three, it's showing how fast the ball is moving. These ones are blank. And then we have the time that the ball has been falling in each of the cases. And in this situation where the ball is just being dropped, just like literally let go of, the acceleration it's experiencing is acceleration due to gravity, and this is called free fall acceleration. And acceleration due to gravity is 10 meters per second squared, or 10 meters divided by, 10 times meters divided by seconds squared. Sorry, lost my train there. And it's indicated by this little g, lowercase g. So here, this is our equation from the previous page, but now we're using variable labels. So we have velocity acquired, right, which is just represented by v here. We have acceleration, which is given by little g because it's acceleration due to gravity. And then we have time here. So we have our ball dropped from the cliff, and we also have those speedometers, as I mentioned. And so at the beginning, the velocity is 0. So right when it's let go of, it doesn't actually have any velocity. But then as it travels for 1 second, the velocity goes to 10 meters per second. And then at 2 seconds, it's at 20 meters per second. And then we're supposed to fill in these three here. Okay, we're going to try writing it on here. Let's see how that works. So for at 3 seconds, we have the acceleration due to gravity, right? 10 times meters per second squared, right? So that's the velocity, or sorry, the acceleration, which is little g. And then we want to input our time. So at 3 seconds, our time is 3 seconds. So 3 times 10, that is going to give us 30. So the speed or velocity, it's both of those actually at this point. At 3 seconds is 30 meters per second. And then we just do the same thing for each of those. So the next one, instead of 3, we'll have 4. So that'll put us at 40. And then at 5 seconds, we'll be at 50. So we can see how we can use that relationship for acquired velocity to figure out how fast our object is moving as it falls. You can also relate the distance traveled to the acceleration and the time. So I have the equation for this spelled out for you and then like in variable form. So we have the distance traveled is equal to 1/2 times the acceleration times the time times the time. And what that looks like, distance traveled is this little d, 1/2, that part's the same. G, that's the acceleration due to gravity or free fall acceleration, and then times time multiplied by itself. I'm not going to try and say times. No, that doesn't make any sense. Okay, is this here. Time with a T and times itself is squared. So we can figure out, on top of figuring out how fast it's moving, we could also figure out how far it has moved. So we could try that. Let's try that for at 2 seconds. So it's going to be 1/2 times 10 meters per second squared. Meters second squared. Thanks for bearing with me while I write with my trackpad. And 2 seconds, and that itself is squared. So that's going to give us 2 squared is 4. And 1/2 of 10 is 5, right? So that gives us 5 times 4. And so that's 20. So at 2 seconds, our position is 20 meters. There we go. And we know it's meters because this is going to give us seconds squared. And here, let's show that. We have meters per second squared. So this one is accelerations units. And then we are squaring the time. So that's also going to give us seconds squared. So we have seconds squared on the bottom and the top of a fraction. So those cancel, and that just leaves us with meters. So that is all for now. I'll see you at the next one.